Welcome to Homework Lib.
This question contains multiple parts. We have a chemical reaction of 2 moles NO reacting with 1 mole Br2 producing 2 moles NO Br. We are given data at 273 degrees Celsius showing the rate of appearance of NOBr as a function of the concentrations of NO and Br2. To determine the rate law, we need to figure out what the order of the reaction is with respect to each reactant, NO and Br2. To do this, we need to use the data that is provided. It's often helpful when calculating the order with respect to a particular reactant to do a ratio of rate laws. So we'll take the rate for experiment 1, set it equal to the rate constant multiplied by the concentration of Br2 raised to x multiplied by the concentration of NO raised to y. If we choose 2 experiments where one concentration is staying constant, then it will cancel from our ratio of rate laws. The second rate law will come from experiment 2, where the rate is 150 molar per second. Set that equal to K, multiplied by the concentration of Br2 raised to the x, multiplied by the concentration of NO raised to the y. Then you can see that we have common values in the numerator and the denominator that can cancel. The K values can cancel, and the concentration of Br2 raised to its power can cancel. Then when we divide what's on the left-hand side, we get 0.16. That will then be equal to this division, the whole thing raised to the y, which is 0.4. And if you're astute, you'd recognize that 0.4 squared is 0.16. If not, you can take the log of both sides, and your exponent will become a multiplier. Y is now equal to, or y is now multiplied by the log of 0.4. Then you can divide both sides by the log of 0.4, and the log of 0.16 divided by the log of 0.4 is 2, so y is 2. Therefore, it is second order with respect to NO, y referring to NO. Now to determine the order with respect to Br, let's look at experiments 2 and 3, let's look at experiments 1 and 3, where now the NO concentration is staying constant. And again, we'll do a ratio of rate laws. So with experiment 1, we have the rate equal to 24, set that equal to K, multiplied by the Br concentration Br concentration raised to its power, multiplied by the concentration of NO raised to its power, which we just determined is 2. Then we'll look at the next experiment, experiment 3, where the rate is 60, set that equal to K, multiplied by the concentration of Br in experiment 3, 0.5, multiplied by the concentration of NO in experiment 3, 0.1, also raised to its order, which we just determined 2. Now we see that K is common to the numerator and the denominator, as is the concentration and the order for NO, so all of those cancel. We'll then divide 60 into 24, and we'll get 0.40. Then we'll divide 0.5 into 0.2, and we'll get 0.40, but that whole thing is raised to the exponent, x. So hopefully you can recognize that 0.4 is going to be equal to 0.4 raised to the x only if x is 1. So now we've recognized that it is first order with respect to first order with respect to Br2 and second order with respect to NO. Therefore, the rate law will be rate is equal to K multiplied by NO raised to its order 2 multiplied by Br2 raised to its order 1. The next part of the question asks you to determine the average K value for all 4 experiments. Now that we know the rate law, and each experiment provides concentrations and rates, the only unknown for each set of data for each experiment is the rate constant. So let's plug in the values for experiment 1, rearrange and solve for K, and we get 12,000. This is a third order reaction overall, first order in Br, second order in NO. Therefore, the units are going to be 1 over molarity squared time, and time is in seconds. Then we'll do it for experiment 2, plug in the rate and the concentrations that give that rate with their corresponding orders, rearrange it algebraically, and K is equal to 12,000 again, 1 over molarity squared seconds. Then we'll do it for experiment 3, and sure enough, it's 12,000 again. And then we'll do it for experiment 4, and this is no fun, it's 12,000 again. I wish if they had asked you to calculate the average, that they would have given you, instead of some hypothetical data, they would have given you some actual experimental data, because usually it is not exactly the same every time, but it's close. Then the average calculation makes more sense. Otherwise, in our case, it was pretty much a waste of time. The average is going to be 12,000, 1 over molarity squared seconds. The next part of the question is in reference to the rate of appearance of NOBr related to the rate of disappearance of Br2. From the balanced chemical reaction, we see that there's a 2 coefficient on NOBr, therefore it is appearing at twice the rate of disappearance of Br2. This will be important to know to answer the last part of this question, part D, where we will actually calculate the rate of disappearance of Br2. From the data and the rate law, the rate is in reference to the appearance of NOBr. So if we know the rate constant, which we just determined here, and we know the concentrations, we can solve for the rate of appearance of NOBr. Plug in our K value, set that equal to the NO concentration, square it, because it's second order in NO, multiplied by the concentration of Br raised to the first power, and we get the rate of appearance of NOBr at 16.9 molar per second. But based on what we determined up here, that is twice the rate of disappearance of Br2, so Br2 is going to be 1/2 this rate, or 8.4 molar per second is the rate of disappearance of Br2.